machine, and we'll continue in part 2 in 2 weeks. And I hope to be able to present you an index R200 with 2 turrets type B-axis and 2 tables. Very complex machine also. Today we see this Chiron, which we have an upper turret type B-axis with I just need to hide this bar, and I can't. Okay, hide. We have B-axis on upper turret. We have the main spindle, a rotary turret with milling and turning option on 30 degrees, and the spatial device that is we have here on Chiron is a table back spindle, a table kinematic with 2 rotary axes. The first is tilting BT and C. Now the more problems that we have before, and we didn't be able to support this machine, is because the controller is changing the coordinate system for milling and turning. For milling, the coordinate system is, as you see here, Z in up direction, X is horizontal in right direction. But for turning, the controller will change the coordinate system to the standard turning mode. That's mean X up and Z right. Z will be the axis, turning axis. So today we are able to define this machine and to change between modes, between milling and turning in the same machine. But this is the machine that I will present today. The simple part that, because we don't have much time, I will machine. But before that, I want to show you some improvements, enhancements that we do in mounting. Now, to be able to see the difference, I think the best way is to go back to 2013 and see how we do the mounting in 2013 version. And after this, we can see very clear the difference. So I'm going to change the version to 2013 release. And I will open an empty part because I just want to show you on tool table the mounting issue. Let's delete the holder and reset the mounting for now. Now, in the past, in a previous version, when we define a tool and we try to mount a steel holder, it was a process. So we select a turning holder. And let's select, I will select a 45 degrees because here is more complicated to mount. So we have a 45 degrees holder, and now I need to define the shift of origin of the tool, shifting, to mount the tool here in this position on the holder. So generally we know some information from tool data, from topology, shank. We have a 160 millimeters length shank, and we have M, the width of the tool, 32 millimeters. Those are the dimensions that I use when I select a straight chunk. So if I'm going to put here minus 160, information from, and minus 32, the tool is placed. So for a straight chunk is okay, it's easier. But if I'm going to select the 45 degrees, now I need to rotate the tool 45 degrees, and my shift is not good anymore. I need to recalculate the shift. So we have two options to calculate this with sinus and cosinus mathematics with the calculator, or to draw a sketch. Draw a sketch 45 degrees and to get the dimensions. So for Z position we have 135, 76 and 90.51 plus. Now I have the tool mounted. This was the process. We are able to mount the tool, but it was not a very fast and easy process. And also, if I want to change the shank, the length of shank to for one reason or another, let's go to shank, and I will change to a shorter one, 100 millimeters. And now again I need to recalculate X and Z. So we all know the problems, and we start to do this in easier and to develop an easier way in 2014. Now let's go back to 2014 version. And I will open the same part with only one tool in tool table, example 1. Now I have the tool already defined from the previous webinar. I need to delete it and holder, okay, and reset the mounting. 45 degrees to 0. Now, this is the way, this is the position that we get when we define a new tool, a new turning tool, and we see, today we see the coordinate system of the device, of turret, and we see coordinate system of station. It helps us to understand the position in machine space, where and how we see the tool, because we know the machine, and here it's enough to see the coordinate system orientation. Now this is the device coordinate system, and I see as 4 chiron with upper turret with z-axis up and x in the right side. Now I'm going to select the same 45 degrees STL holder and use again the information from shank, 150 and 32 millimeters. Now today we create a new coordinate system. The origin is shifted to the mounting point, and when we rotate with the angle, we rotate the setup angle to minus 45 degrees. The tool is not rotated around the origin point, it is rotated around the mounting point. So in this way, don't need to change anymore the shift for Z and X. I can change the angle. The tool remain in the same point attached to the STL holder. much easier, and I don't need to calculate anything. I just need the information of shank. Minus 45 degrees, and that's all. Now, also if I want to change the shank to another length, 110, I just need to change here again the information 110 with no calculation, and the tool is mounted. Also the flip, if I want a flip, is the tool is flipped around his own coordinate system. So let's change it from, let's make a change to see from right to left. I have a left tool, and the holder is not, I will select the same holder but opposite. Not milling, I'm going to turning. Also here we can see in STL holder database we can define today folders, and to separate STL the STL holders into folders, and to rename the folder by machine, by manufacturer, by anything that you know, any name that you need. So I'm going to take, okay, this one, and 45 plus, and here now the tool is mounted. I change the tool, I change the holder. With a few clicks I have a new tool mounted. A new way, an easier way, a better way. Now also the window of the mounting, we are going to change it to, you will get this in, I hope, in SP3, in Service Pack 3. Now this is the window that we see for a spindle type, but if we define a tool for a rotary table, lower turret for example here, you see that you have more options. You can mount the tool by axis, yes. Mount the tool along Z-axis, Z minus, or Z plus, or X minus, or X plus, and give an additional angle. Instead of icons that we have before, now we are based on a axis direction. This is about tool mounting. Now we are going back to our part, example 2. A little bit information in machine ID. We have 4 devices: upper turret, lower turret, main spindle, and back spindle. On upper turret we have 4 axes, X, Y, Z, and B. On lower turret only 2 axes, main spindle with one rotary axis named A, and back spindle with V. It's an indexial linear axis on Z direction. BT, the tilting, and C, a rotary axis. Now, for turning, we define a submachine with orientation as the controller, with the standard orientation. Z is a turning axis, the X-sub, and for milling, we define another coordinate system. I need to go out from here. I will show you coordinate system. Another with orientation with Z in up direction and X horizontal in the right direction. This is for upper turret on main spindle, the difference between milling and turning. Upper turret on back spindle, lower turret with main, lower turret with back spindle. 5 submachines, and we are going to define 5 coordinate systems. I will hide them, and first coordinate system for turning, as we say, the standard orientation, for milling is, as in any milling machine, 3-axis, 4-axis, 5-axis with Z is spindle direction and X. Mach 3 is upper turret working on a sub-spindle, and the coordinate system is defined when the part is this way positioned, Z up, X right. Cancel what I did. Mach 4 is for lower turret with on main spindle, 30 degrees rotated around Z, and Mach 5 and for lower turret on back spindle with Z direction. We define the coordinate system when the part is on back spindle on reference point, but the turning process will be done in this position on 90 degrees tilting. So the coordinate system will match the axis direction of lower turret, X and Z. This is about the coordinate system. 5 submachines, 5 coordinate system. In the setup, we assign to each submachine his own coordinate system and shift position of Mach related to submachine. So if I want this part to be out of the main spindle 63.6 millimeter, that means the coordinate system Mach 1 position 1 is on Z-axis on 63.6 millimeter distance from the main spindle. And this is for milling. Now, because on milling we have different coordinate system, the shift is automatic. We don't have to put here the value. It's calculated by SolidCAM automatic, and SolidCAM detect the change in orientation and take this shift that I define and put it on X, because now this is X. For back spindle I define 75 and automatically is calculated for upper and lower turret. Each submachine using the same table has a calculated shift. This is about the setup. In this way we define a setup. I didn't define any fixture for main spindle because we have a chuck with collet type, Swiss type collet, so we don't need to define it. Only for a sub spindle I create a 3D design model, jaws to catch the part. It's not a turning part. I don't need here the standard jaws to catch a rounded surface. Here we have a part with planar surface and angles, and so I designed this to catch the part around. And here also I have a surface that match the radius to helps us to catch very precise the part and move it to work on sub spindle. Let's start to see the process. Here I hide. I define a turning operation with upper turret on main spindle just to demonstrate that how we define a turning operation, but it's a milling part, so we can start milling directly. But for demonstration, I use also a turning operation. Let's see, I want to show also the stock and target envelope, which is built automatically by SolidCAM. So we start with the turning operation. We remove unnecessary material, and with a few operations of eye machining, one for this level and the second for this level. In opposite side, another eye machining, and around. I prefer, it can be done also with one job with different dips, but I prefer to do each dip. I have a better control. And face milling to finish this surface, an open pocket to finish this surface, a contour which I only finish half of this circle. I don't want to remove and to break the connection with main spindle. Face milling on opposite side on this face to finish the surface, and again around the part a contour to finish up to again half of this circle. I'm using MCO to retract the turret to a safety point, upper turret, and now I will use lower turret to drill, center drill, and drill those holes. Now, because I don't have a y-axis on a lower turret, it's possible only to drill on the center, and we use 4th axis. Also, the geometry should be defined as around 4th axis. Lower turret, after I finish the drilling process, lower turret retract, and again I come with upper turret on main spindle milling to finish here this from this side the pocket, and from opposite side with a helical contour. Now we have a transfer process from main spindle to back spindle, and the last device that was working here was upper turret, so I sent him to a safety point. And main spindle, I'm entering in a milling mode and movement to 0. A-axis to 0 degrees. I need to synchronize the position on main and back spindle. So rotation axis on main spindle is A to 0 degrees, and also on back spindle the same process, working mode milling and movement to C-axis is rotational axis to 0, and BT to 90 degrees. That means the table will be prepared to advance now in V-axis and to catch the part. Go to this position and catch the part. We can use the functions for back spindle chuck and main spindle chuck, open, close the jaws, for the M code, for the G code, for the program. For the simulation is not needed. Part move, V-axis, go back to reference, and BT axis also go back to 0 to reference. The transfer process is done. Yes. Upper turret on back spindle. Here I will remove with a turning tool the rest material, and a milling operation to finish the remain half circle here. But to make it more interesting, when we work on upper turret back spindle, let's go and see about the definition. Upper turret back spindle. We have this submachine, but we have more axes than we need here. We have 7 axes. So we decide, and the manufacturer decided, working on upper turret on back spindle, we use XYZ from turret and BT and C from table. B axis can be used and V indexial from MCO. But 5 axes involved in submachine, there are XYZ, BT, and C. Now, the last development that we work very hard to do this, I control axes that they are not involved in the submachine with MCO. B of upper turret, I put it on -10 degrees, and let's see what's happened. But I will start the simulation from the start, and we are going step by step. Okay, make the stock transparent. So as I say, we have a turning operation. We remove the material and start with a few eye machining to remove material. Collisions all the time. The machine simulation will check collisions. It's activated. If you don't see the collision, that's mean we don't have here a collision. It's the setup it was done very good. But if I want to check, I check it manually. We see any collision. We can continue. And we remove all the material. Now we start the finishing process with face mill and an open pocket. Now here, let's go back and see. I define the extension entry of geometry, entry and exit, with a little bit more than what we need in order to get a collision. And we see that we get here in report collision between chuck, main spindle chuck, and tool adapter of tool number 2 adapter. We get the report here. Now I define a 2 mm extension. I need to change it to 1.5 and it solved the problem. But I leave it in this way just to see the report. And finish on this surface. Again, a small collision. We have it here. Now, between the operations we have upper turret retract. I'm going step by step, and to see what I define, Z and X, Z and Y axis together, and X and B simultaneous. And this is exactly what I get. What I define in MCO, I get in machine simulation. Lower turret starting with the center drill. And drilling with 6 millimeters and drilling with 2.8 millimeter. Now this tool is the tool that I start to define. I didn't delete it, yes, so ignore it. retract for lower turret to a safety position. And now again the upper turret will finish those pockets with a helical contour, and in opposite side. Retract again, Z and Y, X and B. And we start, we prepare the main spindle rotary axis to 0, sub-spindle, C-axis to 0 and BT to 90 degrees. Now V-axis going to the, toward the part and catch the part. Part move, and BT axis to 0 degrees. Now we talk about minus 10 degrees. Why I define B axis to minus 10 degrees? We see B axis on minus 10 degrees, and in turning operation I define the tool will be perpendicular to turning direction. Now B axis is on 90 degrees, on 10 degrees, minus 10 degrees, and BT is calculating the position, bring the part to preserve the orientation of tool and part. This connection will not be break. I define the tool 90 degrees, perpendicular to, is perpendicular to turning axis. Whatever position I will define with MCO, the BT will calculate and preserve this connection. Now, why we do this? Because it's possible. In machine is possible, and the reasons can be different. A better cooling, a cheap removal, easier, a better view of the user from the window of the machine. I don't know, it's a technological option. If the user wants to work on this angle, SolidCAM must provide him the solution. So we are able to provide the solution. Define any angle on B axis. The BT axis will preserve, will calculate his new position and work, depend on tool direction. For milling, now I define a plus 10 degrees, just to see that is working also for milling and turning. Now plus 10 degrees, the same logic. Also, when we define a position, we define I want to work on this surface. Tool must be perpendicular to this surface. So we are going in some machine and look, what is the position of the tool? What is the orientation? Tool direction is plus 10 degrees. So I must bring the BT on 80 degrees to be tool to be perpendicular to this surface, parallel to Z of position, what we define. So we are able today to mill and turn in any position that we need. And the last operation is going to an end position, to an unloading position. Here the back spindle opens the jaws and it drops the part to unload the part. So this is the way that we work today on, we are able to support the Chiron. I will not lie to you, we have a small problems today with turning on back spindle, only in simulation, but it should be solved in a few days. So for service spec 3, when you will get it, it will be fully supported. And on this part, I didn't have the chance to show you the turning with lower turret, but I have a different part where I can turn using lower turret, and also milling with lower turret with 4th axis. I define a turning operation with lower turret and face 1, and also 4th axis rapid geometry with iMachining 2D. Okay, it should appear now. Yeah. Turning, and it was a long turning, now face turning, and milling with 4th axis. In the same way, we can work also on back spindle. The only problem, we have small problems with turning with the position of the tool on back spindle, but our developers work very hard, and I think maybe it can be ready to the next day webinar. Tomorrow we have also a webinar, and it should be ready. Now, I know that all of you love impellers. You love 5-axis simultaneous. So here we can see an example with 5-axis operation, but is done with in different kinematics. Open. Yes, we have a simple impeller. I do only one job. You see a lot of examples on other webinars, but what I want to show you here is the difference between a head table submachine and a table submachine. The same part I will mount first on the main spindle, and with a different setup I will change the mount and mount the part on the back spindle. Okay, we have it. I will hide the stock. Now here we have an example of working 5-axis simultaneous with a head table kinematic. That means a tilting axis on turret, rotary axis on table. Make it more slower. And let's show also the toolpath. Now the same operation mounted on back spindle have a different kinematic, a table. The both rotary axes are on table. So I'm using MCO to retract the upper turret. Manually we mount with a new setup the part on back spindle, and here we see a different mode, a different kind of movements, tilting and rotary on the table, and it's the same operation. So it's also very important to understand that today we support any kind of kinematics, table, head, on the same machine. We define different submachine. We define the correct axis that we want to use, and we have a different kinematic. Now, with the same machine, I can define another submachine in upper turret with a back spindle, and if I select to use B-axis, upper turret on back spindle, axis order, I can select instead to use BT, the tilting of table, use tilting of turret. I will have again a head table kinematic. B from turret, C from table. It's only a problem of definition. We can do anything. So this is all for today. I hope to see you again in 2 weeks in the part 2 of this webinar, and I want to see you, as I promised, to present you the Index R200 machine, working with two B-axis type turrets, and also 6 additional tools on each turret, turning tools. If you have any questions, I can answer now.
Thank you, Florine. Does anyone have any questions? Okay, so I see everyone is good. I hope you enjoy the rest of your week, and we will see you in a couple of weeks.
Thank you very much. Bye-bye.